We're looking forward to your talk, and thank you for being with us.
Thank you very much.
Yeah, thank you very much. Thank you for the nice invitation. I'm quite happy to be here. I'm more happy that you're all here. The topic we're trying to talk about today, or we're going to talk about today, is well, the idea is, well, let's just start to the next slide, is to change perspectives. Because we're often talking here about technology. And I think talking about technology is only one part of the coin, but we should also talk about the user. Okay, so the first part of this talk, which we cannot see right now.
It's on the screen.
It's on the screen. Okay, thank you very much. So the first part of this talk is about the idea of changing the perspective. Okay, so getting into the perspective of the user. And we know there is different types of users. And a user we often know, and which is quite impressive, is a big tech company pairing up with the perfect use case provider. And these are specific examples that we often see where we say, wow, that's pretty nice. So they have extremely high QC expertise, they have very high resources, and they have probably the best use cases, or very high interesting use cases. But the result might be very narrow. I mean, it's pretty nice to argue why the technology is important, why we can continue, but where is kind of the profit for the company? On the other side, we have often, well, say, cross-industry operations and taking their learnings in order to step forward in quantum computing. So by the way, this clock here is only blinking. And there is the hope for the lucky punch. There is QC expertise, which is medium, low. There is resources probably high, and there is the quantumness of the problem is medium. This is the kind of POC that we get at the end often, and this is where we also don't want to end. We want to see what the real user wants, and the real user might be a company that really wants to learn, wants to use quantum computing, but doesn't know how to use that technology. And what are the different steps that are needed here? The experience in QC is right now rather low, resources are medium, and the quantumness is potentially high, but they have to figure out. So our idea is to ask the question, how to help these people over here. So let's just get into that companies, and of course they have a lot of questions. They see quantum computing, what is that? How can we use that? And what are, I mean, it's the same questions that we always state at this point, how to make profit out of that. And for these companies, would be nice to give them some help, to give them the ability to have a plan, how to do these things, how to check out, how to run around this kind of, well, this treasure search. And at the end, empower them to be able to try as many potentially great use cases as possible. So in order to understand how to do that, we need to understand how these companies work. What do they do usually? They start with the identification phase. They want to identify a problem and they analyze the problem. And usually they know how to do that. In QC, they don't know how to do that. So in the first rounds of this iteration, they need some help. And this is where we kind of need to consult them, tell them, look, this is where you can learn, but after a few rounds, they know how to do that and they can do it on themselves. So we need to empower them over here. The same, and this is more like the technical perspective, is how to then list the potential models. How can I take the identified and analyzed problem and get out of that potential models where I can model this problem in and to choose a model. Okay, and here we need more the technical QC knowledge that is kind of needed to be transferred to these players. And then there is something they know how to do, is the modeling of the problem. And this modeling, well, is problem knowledge. Of course, they have a lot of problem knowledge and they have modeling skills, but not in QC. So again, we need here some round of help. And at the end, it needs to be implemented. Implementation of the model and implementation and test and benchmark of the code. And therefore, very high, I mean, usually nowadays, very high QC implementation skills are needed. Hardware characteristics are needed to be understood. It's not only quantum physics 101 which is needed, it's really quantum mechanics details that are needed in order to understand how to get this done in a very nice way. And then benchmarking is pretty hard, apples and oranges at the end. I mean, how to do that? We have here the numerical recipes in Fortran. I mean, this is the kind of idea, and at the end, you still don't know whether your algorithm is working in the best way it could. It would be much nicer if there is real expert doing that job for you. Of course, we have the quantum algorithm zoo, which is kind of the transference of these ideas to the quantum world, but still that needs to be done. Now, what would be nice? What would be nice if we could do the transformation from the assembler to Fortran that we had in the old days. We have abstraction layers, we have hardware independency, it's easy to use, and we can take advantage of a lot of libraries. And of course, the same doing in a quantum world would be hardware-specific language going to the next abstraction layer, being hardware agnostic, and so on. This is what we're going to show today. The idea of doing these hard steps by Qrisp. Now let's see how these different people then would react. I mean, if we have something that helps in choosing the model, has already predefined implementations done, and has already predefined tests and benchmarks. So the real expert we have here says, well, this is easy peasy, but it helps still a lot, and it's much easier to go to more use cases. Of course, we can continue with POCing, but we can also do that with more effort, with more results. And the person we're really interested in, as I said, needs some help in the first rounds, but then can do this more and more and more alone. Really learn from these steps, can do what is very important, analyze the problem, have all the domain knowledge, and of course then use Qrisp. And as it was said, he is one of the core developers of Qrisp with me, Sebastian, who's going to tell you now details of how to do this exactly in Qrisp, how the advantages of the languages are, and how to do implementation here.
Thank you very much, Uli. That's a perfect transition, as if we had planned that. So we have just seen all the steps we have to take when we want to tackle a specific problem. We have to identify it, analyze it, implement it, model it, and so on. And we want to do this now with a specific example using Qrisp. So before we get to the example, I would just briefly want to introduce Qrisp, and I want to do so with a small programming example, actually. So what you can see now is, well, we start by importing the quantum float class from Qrisp. Experts already see, okay, it's a Python framework, so that's Python code right here. And then we initialize two variables, A and B, of type quantum float. Each of these variables gets 3 qubits, so that's the 3 you see in the brackets. Because, well, if we have a float, they have like 64 bits. If we would have 64 qubits, well, most quantum computers aren't that big, so we need to be aware of this. So you can set the amount of qubits you want to use, and the number, well, you can represent increases. So with 3 qubits, you can go from 0 to 7, or, well, then represent also decimal numbers. That's also an option there. So we have two variables now. Now we want to do something with that, and before we can actually do something, we initialize them with 3 and 4. That's what you see in the next 2 lines of code. And then we can actually use them to perform operations. And we just do a very simple operation here. We multiply them, store the result in a new variable called, well, result, and then we want to print that to see what we get. And we get 12. Well, that's expected. That's what we should get when we multiply 3 and 4. But we get 12 with a probability 1.0. So you can see this is not just a normal Python program, but it's an actual quantum program, which very much looks like a normal Python program, what you would do there, but it really compiles down to gate level and qubit level, and then can be run on a simulator, as in this case, for example. That's why we get 1.0. If we would run this on a hardware, well, we would get some different probabilities, but it's a full-blown quantum program, and that's what Qrisp is about, to use quantum variables and functions instead of just single qubit and gate objects, to really get to a higher abstraction layer and to make it easier to implement algorithms and to deal with them. And that's what we want to do now for a use case. So, well, imagine we have some train station, for example, S-Bahn station Treptower Park, pretty close to here actually, and we have some schedule for this train station. So this is around lunchtime now, and we have all trains are mapped to platforms and everything works fine until it doesn't, because, well, we might have some construction work going on there. And one of the platforms is blocked and cannot be used anymore. So now we do have a problem because the schedule does not work anymore when one of the platforms is not operational anymore. So we need to find a new mapping, check if we can find one, if we can, with the leftover 3 tracks, create a new mapping such that the trains can then be mapped to these. So this is the first step. We identified a problem now. Then, well, we'll go further on with analyzing the problem. And, well, that's when problems get more complex, it takes more time right now. Well, we analyzed it, so we need a new mapping. That's what we want to do here. And now next thing is to choose a model. And we want to use a graphical representation here. What we do is we assign nodes to each train and then connect these nodes whenever there's a conflict, meaning these trains cannot go or cannot use the same platform because, well, they are too close together in time or they go in different directions, then we have conflict. If we map this now to a graph, for this example, this looks something like this. So now we have a graphical representation, or you can also display this as a list as it is here, which we can then use to implement it in a program, but it's really just the same as the graph you can see. And what we then have is, well, we have to model the problem. So what we want to do is to each node, we want to assign a platform. And since we already have numbers here, we don't want to write a number on top of a number, but we use colors for that. So we assign a color to each node. And what we did here is basically solving the graph coloring problem, which is a very difficult problem actually. It's NP hard and difficult to solve. So if you go to larger schedules, that's well, not really feasible anymore at some point. And I think very recently there was a headline from Deutsche Bahn that they are just estimating the schedules now. They're not even really calculating them anymore. They're just estimating them. So hopefully in the future, I mean, they improve their tracks and have more tracks available. But maybe we can also help with quantum computing on if this gets more complex to really help them, again, calculating schedules. And well, that's the thing we have now. And it works. But as I've shown you before, we might have some construction work going on, and one of the platforms is not available anymore, so 2 of these nodes are not colored. And we now want to check, can we still find a coloring that works such that we can go on operating with just 3 platforms? That's the question. And now we have to find an algorithm which we can use to solve this problem. And I think most of you probably know the QAOA algorithm, or I can imagine that many of you have heard of this hybrid algorithm. We want to use a different one. We want to use a backtracking algorithm, which is quite well known in classical computer science as well. So it's also a classical algorithm which starts from building up partial solutions and then goes to a full solution. So imagine we start by picking red for one of the nodes which is not colored, and then we see, okay, is there a conflict? Well, if there's not, then we can color the second one, and we choose also maybe red, and we see there's a conflict. Okay, so we have to go back, but not all the way back, so because we have a partial solution, and we then try maybe blue. So this is like the backtracking step you can see here in this picture. And it's like a recursive algorithm. The implementation is recursive, but it really goes from building partial solutions to a full solution then. And there's of course a quantum analogon for this, a quantum backtracking algorithm, which is based on quantum walks. So you can somehow imagine that with using superposition, you have the ability to explore many paths, well, in superposition. It's not like that we try out every possibility and then it just collapses to the right solution. That's not how it works. It's way more complex than this. But with quantum walks, you still have the opportunity to explore multiple paths in superposition. And this gives us a quadratic speedup for the quantum backtracking algorithm compared to the classical part. So backtracking algorithm is pretty versatile and can be used for many different problems. So the complexity can also vary depending on which problem we apply this to. And the quantum analogon always gives us a quadratic speedup compared to the classical analogon. And it's rather complex and tedious to implement. So that's something we don't want everyone to do. So that's now where, again, the connection comes in. So the experts, like the big companies, they can be able to do this. They can implement such complex algorithms. They have huge manpower. But smaller companies who are not that well known yet with quantum algorithms, they have a hard time implementing such a difficult algorithm like the quantum backtracking one. And that's something where we can help because we have already done this in Qrisp, in our programming language framework. And when you go to this QR code here, there's a very nice tutorial where we explain how you can use the quantum backtracking algorithm to solve a Sudoku puzzle. And now you might think, okay, well, but we want to solve a train station scheduling problem, not Sudokus. It's nice, it's fun, but not a real world problem. And if you go to the website, so you see the quantum backtracking, and then you see the tutorial. Is it not working anymore? Okay, I would like to go on, but can we go to the next slide? Yeah. Ah, okay, then just the screen here is hanging. Okay, sorry. Yeah. Okay, I was clicking a lot. Okay, sorry. Then this screen is stuck. Okay. Well, I have to take a look then on the screen. So okay, we go to the we go to the website, to the Sudoku example, and then we scroll down a bit, and we actually see, okay, now it's working again. We have a mapping to a graph coloring problem, which is exactly the problem we want to solve. So, as I said, it's a versatile problem set and can be used to tackle many different use cases, and also our use case. And when you go through this tutorial, that's really nicely explained of how this works. You can pretty much just copy-paste the code that is written there, adapt a few things, like of course we have to use the graph we just implemented for our use case, the amount of colors that are available, in this case, well, just 3, not 4 anymore. And if we then run this on a quantum simulator, you really get a new mapping, and for this case, it works. So with just 3 tracks, we are still good to go. And this is really just a small toy example, of course, but it shows nicely how this could be used then to scale to bigger instances. And that's really problems we have. And just to summarize all this, how this connects now with the whole the whole solution of how we can tackle problems. So first step, of course, is to identify a problem. There are many different problems you might face, but you still have to somehow also really analyze and isolate them to really make it possible to then map this to some model, to some mathematical representation, what we did here then with a graph representation, and then to, well, be able to map this to a graph coloring problem. And we have to add all the constraints, of course, well, if they can't use the same platform. And then, well, we have to start implementing it by adapting this for the framework we want to use. And that's where a framework should help you by already having pre-implemented the complex algorithms such that you just need to adapt it for your use case and then easily run it, ideally on a simulator, which is built in. Also in Qrisp, it's built in. So we can start doing some easy testing, what we did here. And then next step, of course, would be benchmarking compared to classical implementations already to other algorithms. And that's, well, how you can tackle problems. Thank you very much.